I
Yeah,
hope we are all fine. I'm going to request someone to lead us in a word of prayer. Yes, Trisha, you can pray.
let's all humble ourselves for a prayer. Our Heavenly Father, we thank you for the gift of life. We thank you for today. We thank you for today's lesson. May you provide us with knowledge, understanding, and wisdom. And may we understand each and everything that is taught. May we not forget it. May you provide us with good memories.
Thank you so much, Trisha, for that time of prayer, but you just went off. I don't know if you had concluded that prayer. Okay, so we are going to start from where we stopped, but before we do that, I just wanted to share with us briefly a devotion before our lesson kicks on. We are God's holy children, Ephesians chapter 1, verses 4, just as he chose us in him before the foundation of the world, that we should be holy and without blame before him in love. Some people think it's the angels in heaven that are God's holy children. No, everyone who is born again is a holy child of God. That means you're one of God's holy children if you're already born again. That's why Paul the Apostle calls holy brethren partakers of the heavenly calling when we read Hebrews 3:1. Don't be surprised, being holy isn't a result of what you do, but who you are. To be holy means to be separated unto God. Jesus Christ separated you unto God. That means you belong to him through Jesus Christ. That means you are holy. Isn't that beautiful? So do holy things. Always remember who you are through God's word and live that way every day. So we have a let's pray. Dear Heavenly Father, thank you for separating me and making me holy and righteous. In Jesus' name, amen. Okay, thank you for listening. So we are going to dive into today's lesson. I see Danisha requesting for a recap. If it's really going to be a very brief recap, otherwise you will need to go and watch the YouTube recording of our previous lesson because it was a 2 hours lesson, so we could not be able to recap that whole thing. So I'm going to ask Aris to help me in case someone has put up their hand or there are any queries in the chat or any responses, since I may not be able to keep checking when I'm screen sharing. So you please assist me there. That's why I made you a co-host. Okay, so you're welcome,
All
everyone.
right.
Thank you. So we are going to do a brief recap, but of course dive into what we have to learn today. So I left us a calculation number. I don't know how many of us tried it out. So Danish, last week we looked at, and those who are just joining us today, we looked at the different enthalpy changes. And among the enthalpy changes we looked at, we had the, we also noticed that for every chemical reaction to take place, it has to be defined in a certain type of reaction as either endothermic or exothermic. And we looked at what exothermic reactions are and what endothermic reactions are. And of course, we also looked at standard enthalpy of formation as one of the types of enthalpy changes. And as you hear the word formation, that means we are looking at the enthalpy change that occurs when products are being formed. But because it's a standard enthalpy, that means it has to be at standard temperature and pressure. So your definition must capture those. And also you need to know that it is 1 mole of substances being formed. So that means whatever you're forming, if you're referring to it as enthalpy of formation, it must be as a result of 1 mole. So whenever you have reactants, they should form 1 mole of that particular compound. That is what we call standard enthalpy of formation, which is denoted as delta T theta F. And then, of course, we also noted that the enthalpy of formation of elements at standard conditions is 0. So for enthalpy of formation of elements, we always denote it as what? As 0. And then for compounds, depending on what has been given to us, we can always find it or use that enthalpy of formation. And then also, we noted that the enthalpy of formation of a substance depicts whether it's stable or not. So if we have a negative enthalpy, that means that compound is stable. If we have a positive enthalpy of formation, that means that compound is unstable and is likely not to occur. So we had a few examples there on enthalpy of formation, as you can see on your screen. And then we also looked at standard enthalpy of combustion. We all know combustion is burning a substance in oxygen. So that means the standard enthalpy of combustion, here you're burning 1 mole of a substance under standard conditions of temperature and pressure. So we had some examples of carbon plus oxygen to give us carbon dioxide. So that is one example of enthalpy of combustion. There is complete burning of that given substance in oxygen. And then, of course, we looked at the experiment, which I won't dive into. So anyone who missed out on that explanation, please rewatch the YouTube recording. It's there on the Holistic e-learning platform. Okay, so we also looked at the different laws, and these ones we basically use them during our calculations. For example, the laws of thermochemistry, the first law we looked at was Laplace law, and we said it states that the amount of heat used to decompose a compound into its elements is equal in magnitude but of opposite charge to the heat given out when a compound is being formed. So when a compound is being broken into its constituent elements, the enthalpy is positive. But when the compound is being formed from its constituent elements, it has the same value but different signs. So you realize that for the formation of that particular compound, it's a negative enthalpy, while for the breaking of that compound into its constituent elements, it's a positive enthalpy, but the values are the same. So that is what Laplace's law states. And then we also looked at Hess's law, where we said no matter the path taken by the reaction, will still arrive at wherever we want to go. So it states that the enthalpy change of a given reaction is the same whether the reaction takes place in one step or in a series of steps. And I gave an example. For example, maybe if you're coming from your home to where you school, you realize that there is that one straight route that you could literally use to get to school. But there are also those shortcuts. For example, people who use longer distances, you realize that one route may have a lot of jam, and then your parent has to take a diversion, but you'll still arrive at what? At school. So it's the same thing with Hess's law. No matter the path taken by a given reaction, whether in one step or in a series of steps, at standard temperature and pressure, you'll still have the same enthalpy change. So we did some calculations, and I had left us with a calculation. So I hope we were able to do that calculation. So today I want us to look at the different enthalpies, and then of course we'll dive into some calculations. But before we go into those calculations, I want us to really pick up from this part of standard enthalpy of atomization. So when we are looking, you'll forgive my background noise. I didn't carry my earphones, so it may be a bit noisy at some point, but please, I hope you're able to bear with me. So we have standard enthalpy of atomization. So standard enthalpy of atomization is basically the heat required to convert a substance in its normal physical state. We say the normal physical state is whereby if we say sodium, that's solid. If we say chlorine, it's in gaseous state. So that's its normal physical state. And under standard conditions of pressure and temperature into 1 mole of a gaseous atom. So here you're converting a substance in its normal physical state under standard conditions of temperature and pressure into 1 mole of a gaseous atom. And we have an example here. So this enthalpy of atomization basically works on already gaseous atoms or liquid atoms. But of course, in some questions, you'll find that some solids have been given enthalpy of atomization. That's why I included sodium here. So you have, for example, sodium, which is a solid being converted into a gaseous atom. And remember, it's 1 mole. And then for chlorine, we have it as a gaseous atom, but it is being converted into 1 mole of a gaseous atom. So that is what standard enthalpy of atomization means, and it is usually denoted as delta HA, small a. So that is what denotes the enthalpy of atomization. And then we have enthalpy of sublimation. Enthalpy of sublimation is more like enthalpy of atomization, but the difference here, this one only deals with solids, because if you can remember changes of states of matter, we looked at sublimation, conversion of a solid straight into gaseous state, or the reverse, gaseous into solid. So here we are basically looking at solids whenever we use the word enthalpy of sublimation. So standard enthalpy of sublimation is the energy required to vaporize 1 mole of a solid element in its normal physical state under standard conditions of temperature and pressure into 1 mole of gaseous atom. So here you're converting 1
excuse
mole
me,
of
excuse me, teacher. There are people in church that are complaining about the speed. They're requesting that maybe you take it a bit slower.
Okay, sorry about that. And thank you for interjecting. Okay, so should I go back to atomization, or you can pick up, I can slow down at sublimation?
I think
Go back.
they say you can. Okay.
Okay, so I was saying, Okay, so I was saying that standard enthalpy of atomization. The way you hear, most of these enthalpies are actually, their definitions are derived from what they are called. So for example, if we are saying standard enthalpy of atomization, it should ring a bell to your mind that we are dealing with converting whatever substance has been given to us into an atom. So here, that means we are going to have, so it says this is the heat required to convert a substance in its normal physical state. And I said physical state means that if I am dealing with chlorine, for example, chlorine normally we know its normal state is gaseous. Then when we go to oxygen, we know its normal state is gas. Then when we come to sodium, we know its normal state is what? Is solid. So that's what it means by from in its normal physical state and under standard conditions of temperature and pressure. Because remember, we said all these standard enthalpies occur at STP because they are standard enthalpies. That means they are going to occur at standard temperature and pressure. And then that conversion happens into 1 mole. This word is very important. And please don't write it as a figure. Always write it as a word. 1 mole of a gaseous atom. So that means your definition, the arrangement of the words may not really matter, but those different words I've underlined must really appear in your definition. So you could say this is the heat required to convert a substance into 1 mole of a gaseous atom in its normal state under standard conditions of pressure and temperature. And I said for atomization may cut across solid, liquid, gaseous, as long as it's being converted into a gaseous what? Atom. So you notice that initially we had sodium, which is a solid, but it is being converted into a gaseous atom of sodium. Then we had chlorine, which is gaseous. It's being converted into 1 mole of a gaseous atom. So as we go about the calculations, you're going to appreciate this better. You're going to find that we need to articulate those things as 1 mole because of the definitions from which they are derived. So atomization, you must understand that it may cut across. So in some questions, you'll find they've given you standard enthalpy of atomization of sodium. But of course, it may also work for the gaseous and then the liquids as well. So I hope that is clear for that part. Sorry, and then we go to standard enthalpy of sublimation. I've said sublimation from your O-level knowledge where you are looking at different changes of states of matter. You looked at sublimation as conversion straight from solid to what? To gaseous. So it's the same knowledge we apply here. When I talk about vaporizing a solid, that means you're converting that solid into a gaseous atom. So that means this is the energy required to vaporize 1 mole of a solid element in its normal physical state under standard conditions of temperature and pressure into 1 mole of gaseous atom. So that means here you're vaporizing 1 mole of a solid element. So here it is definite that it has to be a solid element when it comes to sublimation. And since we are converting them into gaseous atoms, that means you're going to have 1 mole of that gaseous atom in under standard temperature and what? And pressure. So the only difference with atomization for it occurs for any substance. But when it comes to sublimation, it works with what? With a solid. So we have, for example, X, which is converted into a gaseous atom, from solid to a gaseous atom. And then we have sodium, which is converted from its solid state to a gaseous atom. Same thing will occur with magnesium. We'll have magnesium in its solid state, giving us magnesium as a gaseous atom. And then we can have calcium in its solid state, giving us calcium in gaseous state. So whichever solid you could think of during enthalpy of sublimation, it's being turned into a gaseous atom. People, are we together up to that point?
Yes, we are.
Okay, thank you. So we also have a note here. I want you to carry this. I want you to carry this note with you. Thank you. I want you to carry this note with you until we get to what BDE is. So if you can note it somewhere or even take a screenshot, whichever is easy for you, but I want you to take this note with you until we reach to what BDE is. BDE in full is bond dissociation energy. Bond dissociation energy. So it says the enthalpy of atomization, bond dissociation energy, together with the enthalpy of sublimation, can be used to determine the average or mean bond energy for bonds involving unlike atoms. So this one, I'll explain it more when we get to the calculations, but I just wanted you to have it at the back of your mind that when we have the enthalpy of atomization and then the bond dissociation energy, together with the enthalpy of sublimation, it is used to determine the average or mean bond energy for the bonds involving unlike atoms. So I hope we are together. Just take it down. When we get to those different points, I'll explain what this NB means. But I just wanted you to capture it. So moving on to the next slide. Bond enthalpy or bond energy. So when we are looking at bond energy, the same way you hear the word bond, that means we are dealing with bonds, the energy within the bonds during their formation or during their breaking. So we have bond enthalpy is the standard change that occurs when 1 mole of a covalent bond is formed from its constituent gaseous atoms. So bond enthalpy can be defined as the standard change that occurs when 1 mole of a covalent bond is formed from its constituent gaseous atoms. So in this case, you're going to have, for example, if I have silicon plus chlorine gas giving me silicon 4. Silicon tetrachloride. So if I have this, that means I have so here I am looking at bond energy of formation because I am forming a covalent bond from constituent gaseous atoms. So the constituent gaseous atoms here, we are looking at silicon and then we are looking at chlorine. So when these two come together, they are going to form a compound. So when they form a compound, basically they are forming bonds with each other. So that means you're going to have bond energy of formation. So bond enthalpy comes in 2 terms. It can be defined as bond dissociation energy and it can be defined as bond energy of formation. So if they have not specified which bond energy you're defining, you can define it in either way. You can give one of the definitions. But if they specify, you define according to how it has been stated to you. So this one is denoted with a negative value of enthalpy. And then when we go to the next one, it says, is the heat change that occurs when 1 mole of a covalent bond is broken into its constituent gaseous atoms. And this is bond dissociation energy because it involves breaking down of those bonds. So if silicon tetrachloride was broken into its constituent elements, that means in that case, we have broken the bonds between that structure, and therefore it gives us the bond dissociation energy. So us obtaining back the reverse of this one here is what gives us the bond dissociation energy, because we've created bonds within elements of the same kind rather than having different elements forming a particular bond. So is that clear as well?
Yes.
Okay, thank you. So bond dissociation energy is also abbreviated as BDE. So when you meet BDE anywhere, you just could put that into consideration. So we've said bond energy of formation is denoted as a negative enthalpy. So that means the bond dissociation energy is denoted as a positive enthalpy. So that means if we have hydrogen and we are breaking the bonds between hydrogen, that is to give us. So you realize that we've created 2 hydrogens here. This is what is trying to communicate. So we've broken that bond and we've created 2 hydrogens. And that is why we have 2 hydrogens at this end. So that means if I have, for example, chlorine, it's going to give me a chloride and then a chloride. And in some equations, you'll find it written as 2 chlorides. So in this case, that is bond dissociation energy. And that bond dissociation energy is positive. So also you have to note that it can be written that enthalpy of atomization is half the bond dissociation energy. So we have it stated here, the enthalpy of atomization is equal to BDE divided by 2. And then, of course, if the reverse is true, if we're given BDE, that means we would say BDE is equal to 2 enthalpies of atomization. Because we've said when you're looking at enthalpy of atomization, we are looking at the conversion of that gaseous atom of that given substance into 1 mole of a gaseous atom. So you realize that atomization has to do with 1 mole of that given gaseous atom. But when it comes to the BDE, we look at what bond is formed by that given atom or that given substance. So that is why we come in with the atomization energy as BDA divided by 2, and then BDE as twice the atomization energy. And of course, as we do the calculations, you're going to take note of some of these and how they come about and why they come about the way they do. That's clear.
In the chat, Lino says that he's lost.
Okay, is it possible for her to unmute and tell
Oh, Lino, unmute. Okay, doesn't seem to be unmuting.
Okay, maybe let me just repeat that once. again, and then I'll proceed to our calculations. So I was saying that when you're given BDE, remember we've said BDE involves breaking of bonds, of covalent bonds to form gaseous atoms. So in this case, we say enthalpy of atomization is the same as you getting that enthalpy change that occurs when one of the gaseous atom is formed from elements in its normal state and at STP. So that means if I had, for example, chlorine gas, its enthalpy of atomization is going to be 1 mole of chlorine. So that means I'm going to have this. But when it comes to bond dissociation energy has chlorine as this, and then it is showing me how many chlorines exist to form a bond. So that means in that case, I have, for example, I could write this as 2 chlorides to show that there is a bond holding those 2 chloride atoms together. So you realize that at this point, when I am getting the enthalpy of atomization, the enthalpy of atomization is going to have the BD. And then if I am getting the enthalpy of the bond dissociation energy, that means if I have the enthalpy of atomization of this chloride, I have to multiply it by 2 in order to get the bond dissociation energy. And the reverse is true, because you know in math, if I multiply it by something to get the other part, that means to get the other part, I need to divide by 2 to get back what I had initially. So it's basically that's the logic. And I hope maybe if you've not picked it at this point, you could pick it in the calculations. So is that clear for every one of us?
Yeah.
Okay, thank you for that feedback.
Yes.
Thank you. So we are going to do some calculations, and like I did last time, I am basically going to share the question because I wasn't able to type the questions because of the technicality they required me to use at that point. So I'm going to share my whiteboard. Of course, as I read out the question, you can write it down because what I'm going to do is just to note down a few things that I might also need while we calculate. So the question says, the standard enthalpy change of formation of silicon chloride Please, Isaac, can you stop writing on the whiteboard? So the standard enthalpy change of formation of silicon chloride is -10 kilojoules per mole. Rachel, please don't write on the screen. So we have the standard enthalpy change of formation of silicon chloride is -610 kilojoules per mole. Then the standard enthalpy of atomization of silicon is equal to +338 kilojoules per mole. Please ensure that you're noting down the question. Then the enthalpy of atomization of chlorine is equal to positive 122 kilojoules per mole, respectively. So we have the standard enthalpy of change or formation of silicon 4 chloride is negative 610 kilojoules per mole. Then the standard enthalpy of atomization of silicon is positive 338, and that of chlorine is positive 122 kilojoules per mole. And then part A says, use these values to construct a Born-Haber cycle. Use these values to construct a Born-Haber cycle for the formation of silicon 4 chloride. For the formation of silicon 4 chloride from its elements. Use the values to construct a Born-Haber cycle for the formation of silicon 4 chloride from its elements. And then part B says, calculate the average bond energy of silicon chloride bond. Calculate the average bond energy of silicon chloride bond. What is the average bond energy of silicon chloride bond? So we are going to start with the Born-Haber cycle, and of course the Born-Haber cycle is always quite easy because you look at what information has been given to you. The information you have is what determines someone is asking for the history link. Can someone help him get it from the WhatsApp group?
It was shared. Let me see
Sorry?
it.
Okay, thank you. So, I'm still saying when we are drawing the Born-Haber cycle, you use the information that has been given to you. So first of all, we are forming silicon 4 chloride. So we know that silicon 4 chloride is formed from its elements. So basically we have, thank you, Aris. So we have silicon here. Okay, so we have silicon plus chlorine gas giving us silicon 4 . There is a question that has come up in the chat. What's that question about? I've not been able to capture it.
Why does the enthalpy of atomization have both signs?
Have what?
Have both signs. That's from Hilda.
Okay, anyone who can answer that? Why does it have both signs? What do you mean by both signs? I don't seem to get what your question is about.
Maybe Hilda can unmute and clarify.
Okay, if she's there, she can please unmute and tell me what she means by both signs. Because I think I gave both of them as positive. This minus sign here, I think someone wrote on the screen,
Yeah,
but
that
it's a
was her
positive.
query. She
Okay,
was
thank
asking
you.
whether it is possible.
Okay, thank you. So let's continue. So I was still saying when we are looking at the Born-Haber cycle, we use the different enthalpies that have been given to us. So we've been given the enthalpy of atomization, and we say Born-Haber cycle is more like a cycle. So that means you draw the diagram in form of a cycle. So we have enthalpy of, was it atomization or sublimation? So we have silicon to give us silicon in gaseous state. So after giving us that silicon in gaseous state, we have its enthalpy of atomization. Don't remember what I read in the question. So we have it as that. Then we have the one for chlorine, but remember we need to balance this equation because there are 4 chlorides this side. That means you are going to add a 2 here. Because remember, enthalpy of formation is the formation of 1 mole of a compound from its constituent atoms. So at this point, we are going to have the chloride, and I've given us the enthalpy of atomization of chlorine. So this is where I'm going to apply the other concept. Remember here we've been given the enthalpy of atomization, but down here, we have silicon 4. So that means we need 4 chlorides down here in order for us to balance with what is up here. Because remember, we have 4 chlorides bonded to this silicon atom. So we have a chloride here, a chloride there, and there. So you realize that for this equation down here to balance with the one on top here, that means we need to balance these chlorides to make them 4. But still, when you look at these chlorides here, we have a 2 in front of the chloride, and then we have a 2 of the chlorine being at the atomic atom. So that means we are going to balance this by adding a 4 here. So that creates 4 bonds within that chloride atom. So in this case, you need to also understand that we have the atomization energy that has been given to us. But remember, chlorine already we said when we have the chloride being converted into its gaseous atom, that means we have the bond dissociation energy here, which is creating the chloride and the what? And the chloride. But remember, these bonds are existing as what? As 2 bonds already. So that is why we have a double chlorine here. So that means in this case, we are not going to use atomization energy, but we are rather going to use bond dissociation energy because those bonds have been what? Have been broken. So that means you're going to have 2 BDE. You're multiplying the atomization energy. So at this point, because you have, sorry?
Teacher, a question has come up in the chat. A question has come up in the chat, asking whether silicon 4 chloride is a liquid.
Isn't it in solid state at this instant?
Maybe, but people seem
So
to suggest otherwise.
in this case, it's existing as a solid rather than a what? A liquid.
Oh, all right.
Okay, so we have I'm still saying that means we are multiplying the BDE times 2. And since we are forming the bonds as, so we already have the chloride atom as ClCl. But then to balance what we have on this other side, we had that 2 in front of the chloride. So that means there are 2 chloride bonds. That means you're going to have chlorine to chlorine, then chlorine to chlorine to give us the 4 chloride gaseous atoms. So that means after multiplying the BDE by 2, you're still going to multiply actually this is atomization energy. You're multiplying by the atomization energy here. So that means you have 2 atomization energy multiplied by that 2. So I don't know if you've got that at that point.
Yeah, yes.
Okay, good. So after denoting that, we are going to have, you realize that this side we have 4 silicon to chloride bonds, as I illustrated earlier on. Realize that silicon is going to form 4 bonds with chlorine. So you're going to have silicon as the center atom, and then chlorine is bonded with it on either sides, forming a tetrahedral shape. So you're going to find that each of those bonds is considered as a separate bond. So you're going to have silicon, silicon chloride, silicon chloride, silicon chloride until you form the 4 bonds of silicon chloride. So after that, from Hess's law, remember we said it doesn't matter if you take one step or different steps. Remember, we get the enthalpy of formation as, so we have enthalpy of formation, standard enthalpy of formation is equal to the atomization energy of silicon plus the atomization energy of chlorine and then plus the enthalpy of formation of those 4 bonds of silicon chloride bond. Of silicon chloride bond. So you realize that here what we are doing, what we get in one step, we can also do when we add the 3 steps that we have down here. So that means in this case, you're going to have enthalpy of formation was given to us as -10, which is equal to the enthalpy of atomization of silicon, which was given to us as +338 plus 4 times the enthalpy of atomization of chlorine, which was given to us as 122, then plus the enthalpy that was given to us. So here, in order to form these 4 bonds, this one becomes a minus. And I think I explained that in the other exercise we had last time. So if you choose for the arrow to change, for example, remember we are forming silicon chloride bonds. That means this arrow is going to be facing down. Yet we are looking at enthalpy of formation of silicon chloride. So that means if it's facing down, it will have to change the sign to become a negative sign. So that means in this case, we are going to have negative 106 is equal to 338. What is 4 times 122?
480.
400?
88.
88. And then when we add them, what do we get?
$826.
826.
826.
Thank you. So this 4, we are going to take this one, this side, and then this enthalpy of formation will cross the equal sign and also become a positive. So that means you're going to have 4 silicon chloride bonds is equal to negative, sorry, it becomes a positive 10 plus 826. What does it give us when we add?
$1,436.
Okay, thank you. 1436. So since we are getting the average bond energy, that means we all know average in math. You divide by the number of items. So since it's 4 items this side, that means you are going to have enthalpy of formation of the silicon bond is equal to 1
That's 359.
359 kilojoules per mole. And that becomes your enthalpy of formation of the silicon chloride bond, the bond energy of the silicon chloride bond. So average, that means you get the total number of those bonds, divide by the enthalpy you've attained, and that will give you the answer for that particular number of bonds that you're working with. Okay, so I'm going to give us a number to try out. So let's note down this question and try it out and see what we get. So it says, given the following, given the following: enthalpy of atomization of carbon, enthalpy of atomization of carbon is positive 713 kilojoules per mole. Is positive 713 kilojoules per mole. Then bond dissociation energy of hydrogen gas. Bond dissociation energy of hydrogen gas is positive 436 kilojoules per mole. And then enthalpy of formation of methane gas is negative 63 kilojoules per mole. So you're going to draw the Born-Haber cycle and then use the Born-Haber cycle to calculate the mean bond energy in methane. When you're through, you can please share your answer in the chat. Okay, so that's very good. So I'm seeing the responses. 142 kilojoules per mole. But I've seen a different answer here, which is 630. Hilda, I don't know where you've gone wrong. Okay, yeah, 412. Okay, so that's the response that we are all supposed to have, unless someone has a question or something different from what we have there. Okay, so I want to give us a question to try out later. It may not be now, but you could try it out when you create that time. Because if I say free time, someone may say, me, I don't have free time. So later when you create some time, ensure to do this question. Okay, I don't know what happened. Sorry about that. So, Harris, you can co-host me so that I can share the whiteboard. Thank you. So, I was saying we can write as I get the whiteboard on the enthalpies of atomization. The enthalpies of atomization of some substances are given in the table below. In the table below. And in that table we have substance. Then we have enthalpy of atomization in kilojoules per mole. So the substances, we have silicon, we have fluorine, we have chlorine, we have hydrogen, and then we have nitrogen. So for silicon, the enthalpy of atomization is positive 450, positive 450. Then for fluorine, is positive 7939. Fluorine is positive 0.7939. Then for chlorine is positive 121. For hydrogen is positive 218. Then for nitrogen, positive 472.68. Hydrogen, positive 218. Nitrogen, positive 472.68. So have we all captured that? Because I want to read the next question. I'm not going to be writing this one, so please follow through. It says, use the above data to calculate the following, part A. Use the above data to calculate the following, part A. Part A. Average silicon fluoride bond. Average silicon fluoride bond energy. Average silicon fluoride bond energy. Given that the standard enthalpy of formation, given that the standard enthalpy of formation of silicon 4 fluoride is negative 1614.9 kilojoules per mole. Given that the enthalpy of formation of silicon 4 fluoride is negative 1614.9 kilojoules per mole. And please, the units are very important. Don't forget them every time you're working out those calculations. Is negative 1614.9 kilojoules per mole. So your expected answer there is going to be, you can jot down the answer such that when you're calculating in your created time, you can always mark yourself. And those who could share your workings, I would love to look at them. Negative 95.62 kilojoules per mole. So that is the expected response. The answer, you can put it in brackets, such that as you're working out, you mark yourself. So the answer there is negative 595.62. And then part B says, average silicon chloride bond energy. Average silicon chloride bond energy in silicon 4 chloride. In silicon 4 chloride, given that the standard enthalpy of formation of silicon 4 chloride is negative 657.0 kilojoules per mole. The average silicon chloride bond energy in silicon 4 chloride given the formation of silicon tetrachloride is negative 657.0 kilojoules per mole. And there your expected response is negative 397.75 kilojoules per mole. Negative 397.7 kilojoules per mole. And then part C. Part C. Average nitrogen to fluoride bond energy in nitrogen fluoride given that the standard enthalpy of formation of nitrogen fluoride is negative 1 to 5.0 kilojoules per mole. Average nitrogen fluoride bond in nitrogen fluoride given that and then the expected answer there is going to be negative 278.62 kilojoules per mole. Negative 278.62 kilojoules per mole. And then lastly, part D. The average hydrogen fluoride bond energy in hydrogen fluoride given that the standard enthalpy of formation of hydrogen fluoride is negative 271.0 kilojoules per mole. Given that the enthalpy of formation of hydrogen fluoride is negative 271.0 kilojoules per mole. And then your expected answer there is going to be negative 568.39 kilojoules per mole. Negative 568.39 kilojoules per mole. So those are the questions you're going to try out. Okay, so with that, have we all finished writing down that? Because I want us to proceed in the remaining minutes to look at something briefly.
Also, you know, someone was requesting for pardon on how the answer 412 was got on the previous question.
Okay, so we could go through that. Is there someone who is willing to take us through? Because I noticed if someone wants to go through, they could actually use the whiteboard to illustrate. Anyone willing to go through for us? Okay, so in the interest of time, we said we had the question was the enthalpy of atomization of carbon is positive 713 kilojoules per mole. And then bond dissociation energy of hydrogen is equal to positive 436 kilojoules per mole. And then enthalpy of formation of methane gas is negative 63 kilojoules per mole. So the first question was for you to draw the Born-Haber cycle because it was the one going to guide you. The elements that form methane are hydrogen and carbon. So that means we are going to have hydrogen plus carbon giving us methane gas. But remember, we have 4 hydrogens here. That means we need to balance the hydrogens this side. Means in this case, we are going to have the enthalpy of atomization of carbon. And we said enthalpy of atomization is a conversion into a gaseous, 1 mole of a gaseous atom. So enthalpy of atomization here is 713. Then for hydrogen, we have hydrogen gas being atomized. So, but because bonds are being created within this hydrogen, like I explained for chlorine, that means we initially had hydrogen to hydrogen bond. But now there are 2 bonds of that hydrogen to hydrogen bond. And that is why when we get the BDE, we say 2 into 2 times the, sorry, since we're given the BDE here, we just go ahead and say BDE times 2. Because remember, the question gave us the bond dissociation energy. So because it gave us the bond dissociation energy, and of course we know that that bond dissociation energy belongs to 1 mole of hydrogen, and yet there are 2 moles of hydrogen here, that means you're going to multiply it by what? By 2. And of course, to balance this hydrogen here, there are 4 bonds in this hydrogen. So that means you have 4 there. Plus, when you add them, they're going to give you the methane bond. And that means in that case, you have 4 carbon to hydrogen bonds. And because you have 4 to carbon hydrogen bonds, that means you're going to have enthalpy of formation is equal to the atomization energy of carbon plus the bond dissociation energy of hydrogen plus the enthalpy of formation of the 4 carbon hydrogen bonds. So in this case here, you're going to have enthalpy of formation was negative 63 is equal to the atomization energy, which is 713, plus 2 times the bond dissociation energy, which was 436, plus the enthalpy of formation, which we are looking for, the 4 bonds of the chloride of the carbon hydrogen bonds. Then, of course, here we are going to have negative 63 plus, sorry, is equal to, what do we get when we add this side? What is the 713 plus 2 times 436? Okay, 15185. Thank you. Plus 4 carbon hydrogen. So here we are going to have this one cross the equal sign. That means it's going to give us minus 1585 is equal to 4 CH. What do we get here? Thank you. Negative 1648 is equal to 4 CH. So since we are looking for the average bond energy, you divide both sides by what? By 4. So that means you are going to have carbon hydrogen is equal to, what do we get when you divide by 4? 412 kilojoules per mole. And I hope we realize this negative is explained by the fact that we are forming the bond. We are forming the bond from its constituent elements. We said whenever we are getting the bond from its constituent elements, that requires bond formation. And we said bond formation is usually denoted as a negative enthalpy. So that will be your answer at that point. So I don't know if the person who asked the question is now with us up to that point. Maybe she could give us feedback and we proceed. Okay, so we are going to look at predicting enthalpies of reaction. Predicting enthalpies of reaction from, we have 2 ways in which we can predict these enthalpies of reaction. The first one is from enthalpies of formation. And of course, we've already understood what enthalpy of formation is. So we can obtain the enthalpy of reaction. We know enthalpy of reaction is that energy change that occurs when a reaction is taking place. So we can use the enthalpies of formation in order. Okay, thank you for that feedback. So enthalpy of reaction can be obtained, one, by using the enthalpies of what? Of formation. And we know that a reaction only takes place when we have reactants and products. So that means in that case, we can say enthalpy of reaction is equal to the summation of the enthalpy of formation of products minus the summation of the enthalpy of formation of the reactants. So that means in order for us to get the enthalpy of reaction, we must be given the enthalpy of formation of the products and then the enthalpy of formation of the reactants. Like, for example, how you do in math, summation of something. That means if you have more than one product, you're going to get the enthalpies of those two products, add them together, get the summation. And then when it comes to the reactants, the same thing. If you have more than one reactant, you're definitely going to add the two in order for you to get the summation of the enthalpy of formation of the reactants. But this method only applies if you've been given the enthalpies of formation of the products and then the enthalpies of formation of the reactants. So that's the only way you can use this. So we have an example here. It's a calculation. It says, given that example, given that the standard enthalpy of formation of methane, given that the standard enthalpy of formation of methane is negative 63 kilojoules per mole, and that of ethane is negative 84 kilojoules per mole, is negative 84 kilojoules per mole. Calculate the standard enthalpy for the reaction below. Calculate the standard enthalpy for the reaction below. So the reaction is C2H6 plus hydrogen gas, giving us C4H gas, and then of course a 2 there. So we have ethane reacting with hydrogen to give us methane. So we have the enthalpy of reaction giving us, as we've said, enthalpy of reaction is equal to, just give me a minute. So we have enthalpy of reaction is equal to the enthalpy, the summation of the enthalpy of formation of the products minus the enthalpy of formation of the reactants. I hope that is clear. So in this case, we have the enthalpy of reaction as we have only one product this side, and that product is methane. So we are going to multiply the enthalpy this side by 2 because it's carrying a 2 this side. So that means you are going to have 2 times negative 63 minus the enthalpy of reactants. This side we have negative 84 plus, remember what we studied in our first lesson, we said the enthalpy of formation of elements is 0. And you have to indicate that 0. Don't say, in my head, I calculated it was 0. So always indicate that the enthalpy of formation of an element is 0, and always express it in your working. So after that, you're going to get, what is negative 63 times 2? Thank you. Negative 126 minus negative 84 plus 0 gives us negative 84. And of course, this becomes a positive. That means you are going to have, what is the answer there? What is negative 126 plus 84? Thank you, Hadassah. So we have negative 42 kilojoules per mole. And that is the enthalpy of reaction. People, are we together up to that point? Okay, thank you. So let's try out this one and you tell me what you're going to get. Phosphorus, pentachloride, phosphorus pentachloride decomposes according to the equation below. According to the equation below. So we have potassium pentachloride giving us potassium trichloride plus chlorine. So that's the reaction. Given that the enthalpy of formation, given that the standard enthalpy of formation of phosphorus pentachloride is equal to negative 375 kilojoules per mole, and then that of trichloride is equal to negative 285 kilojoules per mole. Determine the enthalpy of decomposition. Determine the enthalpy of decomposition. Determine the enthalpy of decomposition of phosphorus pentachloride. Of phosphorus pentachloride. So please work that out and share with me your response. Okay, so how far have we gone? Were we able to get the answer? Because I went off, I lost all the charts. I don't know what is happening to my network. Maybe if you had worked out, you can share with me what you had got. Had anyone worked out and gotten the answer? Okay, thank you, Hilda. 90 kilojoules per mole. Okay, that's good. Saka, thank you. So the answer is 90. So if you're still lost on how to get it, we said when we are given the enthalpies of formation, we can use enthalpy of reaction is equal to standard enthalpy of formation of products minus the summation of the standard enthalpy of formation of the reactants. So when we have that, that means you're going to say enthalpy of reaction is equal to our products. We had negative 285 plus 0 for chlorine minus negative 375. So this is going to give our enthalpy of reaction, as negative 285 plus 375. What do we get? The answers are already posted. Are positive 90 kilojoules per mole. The one whose mic is unmuted, please can you mute unless you're saying something? So that is going to be our answer. Maybe a take home in regards to this assignment. Let's quickly note down this. Lynette, please mute your microphone. It's making a lot of background noise. Anyway, so as we wind up the lesson, I was saying, let's jot down this question. We'll try them out, and they are just two on top of the other ones that I gave us. And remember, the physical chemistry is all about practice. So don't get tired of trying out numbers. You can, according to what we've so far covered, you can even go to the question bank, look for more questions, and do them. Because the time we have here may never be enough for us to exhaust whatever we need to calculate. So let's write down this question. It says, given that, determine the enthalpy of formation of ethanoic acid. Determine the enthalpy of formation of ethanoic acid. Determine the standard enthalpy of ethanoic acid. So we have substance. Then we have standard enthalpy, of formation in kilojoules per mole. So we have ethanoic acid. The enthalpy of formation is negative 490. Then we have water. The enthalpy of formation is negative 286. Then the enthalpy of carbon dioxide is negative 394. Negative 394. So ethanoic acid burns in oxygen according to the equation below. This is a liquid plus oxygen gas to give us carbon dioxide and water. Plus carbon dioxide and water. Ensure your equation is well balanced because that's when it will give you the correct values. So the expected answer here is going to be negative 87 kilojoules per mole. Negative 87 kilojoules per mole. So please denote that so that you mark yourself. So that is one number you're going to work out. Then the other one will begin it as a review question when we because today is likely to be our last day. Okay, I'll probably share that question on the group, hopefully. Otherwise, thank you all for being a great class, and I wish you the very best as you report back to school. We'll keep in touch. So if you're through with that question, that's all for today. Unless someone has a question, I would want to close the meeting at that. You're welcome, Hilda. Thank you too. And if you missed out a certain point, you're welcome, Caritas. So if you missed out a certain point, please go to the Holistic e-learning platform. These videos are always posted there so that you can relive the lessons and also take down notes. Welcome, Hadassah. All right, so have a blessed time and see you when we meet next. Remember to win and excel, and less strategies for being a success. No one becomes a success by mysteries. So that means you need to work towards being a success. Lay goals, strategies, and ensure that you set goals that you can surpass, not very low standard goals. Okay, someone is asking if on YouTube. Yeah, it's on YouTube. You're all welcome. Thank you too for attending the lessons, and we hope to keep in touch. Okay, but those on the group, you can see my number. It has Martha Light on it. So if you can find it on the group, the better. But I'm going to share it here. So Lynette, if you've captured the number, I would want to close this meeting at this. Okay, bye everyone.